Hello students, in today's video we're going to be working on connecting f and f prime with a graph of f. So let's get started. Go ahead and try these 3 quick practice problems and we'll try them together in a second. Hopefully you've paused your screen and you're just coming back to check your answer now. Now remember, an antiderivative is basically going backwards from what a derivative is. So we have to think about what is the derivative, or if I took something, the derivative would be secant x tan x. And so looking back at my trig functions, we know that the derivative of secant x is equal to secant x tan x. So we're going to do secant x plus c. We always want to do that plus c because we don't know if there was a constant after and it went away when we took the derivative. Same thing with part b. This is going to be e to the x squared. Because remember, if we take the derivative of e to the x squared, that's going to be e to the x, or in this particular case, x squared, times the derivative of the top, which is just 2x. And therefore, we're left with what b is. So this is the antiderivative plus c. For h, this should be a little bit easier. You have to think, this x to the third power was at one point x to the fourth. But for some reason, that 4 that should have been there when we took the derivative. So let me go over that again. If we take the derivative of x to the fourth, that should be 4x to the third power. Now what's missing from what we started with and what we have here is that there is no 4, which means it originally must have had something that would cancel it out, which is 1/4. Because now if we take the derivative of that, derivative of 1/4 x to the fourth, that would just be x to the third. So now we're taking into consideration what's missing. So if we look at the next one, x squared would become x to the third. But since for some reason there is no 3, we have to balance that out by throwing a 1/3 in there. X squared, or the x up here, is missing a value. So when we take the antiderivative, that would be x squared. But what's missing from there is the 1/2. And then the antiderivative of 1 is just going to be x. And again, plus c because we don't know what was there originally. So again, we're going over connecting f and f prime with a graph. And we know that first derivative, now if we take the first derivative at a critical point c of a continuous function, f, now it does 3 of things. 1, if f prime changes from positive to negative at c, then f has a local maximum at c. So you have to imagine that if we have some critical point, if it's going upwards and then at c, which is up here, I'm going to make it a dot, then goes down to a negative, that means it's going to have a local max, as you can see by the graph. Part 2, if it changes from negative, like it's going downwards, and then to positive, that means it's a local minimum. And it says if f prime does not change at c, then f has no local extreme at c. So that means it just didn't change. So first derivative. Now, at a left endpoint a of a continuous function f, it says if f prime is less than 0 for x greater than a, then f has a local maximum value at a. If f prime is greater than 0 for x greater than a, then f has a local minimum at a. So remember when we did these types of graphs at the beginning of the chapter, we had a graph like this and we said, hey, we're looking only at a certain set of things. Now here's our endpoint a. It says that based on part 1, it says if f prime is less than 0 for x greater than a, that means everything after that was decreasing. That means that's why this is the local max. Now if we look at an image for part 2, you'll notice here this is where our endpoint is. And since everything after that is increasing, like it's greater than 0, then f has a local minimum value at a. So I know that seems a little weird, but we'll have time to practice that in a little bit. So at a right endpoint, b of a continuous function says f prime is less than 0 for x less than b, then f has a local minimum at b. And number 2, if f prime is greater than 0 for x less than b, then f has a local max value at b. So again, we'll take a look at some examples. Now concavity is really important. It tells us if a graph is going upwards or downwards. So we'll take a look at some of these graphs. Actually, let's do one really quick right now. If I make a graph like so, okay, and I'm going to change this to blue, it basically says from here to about here, the graph is going upwards, like as in this cave is going upwards, like it's not facing downwards. Notice this whole thing, it almost looks like a parabola like so. Now, from here to about here, this is going downwards because this cave looks like it's facing downwards. This one from here to here is going upwards, and notice I'm stopping halfway between the next ones because at some point it starts to change directions. So from here to here, this is going to be concave down, and this is going to be concave up. Now, that just gives you an image of what that looks like, but we're going to do a couple of problems to put that in more context. Now, concavity tells us when the graphs are going upwards or downwards. Now, I told you we stopped at the middle point. Now, those points are called the points of inflection. Now, it says a point where the graph of function has a tangent line and where the concavity changes is a point of inflection, also called an inflection point. Points of inflection can occur but do not always occur where y double prime equals 0 or y double prime fails to exist. So the sign of y prime must change around that point. So we'll do some practice together. So for example 1, they want us to use analytical methods to find the intervals on which the function is increasing, decreasing, concave up, concave down, and then find any local extreme values and inflection points. So there's a lot to do there. So what we're going to do is we're going to just worry about what each piece means, and we're going to work through it, and I'll explain it as we go along. So for the first one, first thing we're going to do is we're going to find the first derivative. So the first derivative here is equal to negative 6x squared plus 12x. So notice all we've done so far is we found the first derivative. Now we find the first derivative, now we set it equal to 0. And we get negative 6x times quantity x minus 2 equals 0. We get x equals 0 and x equals 2. Now these are our critical points. Yes, these are our critical points. Now what happens with these critical points is they tell us where our max and min is, where they are. It also tells us where this graph is increasing and decreasing. So think back to your pre-calculus days and look at this first lead coefficient here. First of all, this is an odd graph. Now odd graphs either end like this or like this using their end behavior. This tells us what the left side and the right side is going to look like. Next thing we do is we look at the lead coefficient. Since this is a negative, that means it's going to be going downwards at the end. So this is what the graph should look like at its ends. So if you could imagine, we have a graph that's going to be going downwards, and because we have two critical points, it's probably going to go upwards and then back downwards. The other thing that's great is that this 3 up here, this exponent, tells us how many times it changes directions. So let's look at the graph at the bottom left again. Notice it's first going down, then it's going up. So it changes once, twice, because it was going down, then up, and it's going down again. So that's the third change. So this is a very, very rough sketch of what the graph's looking like. Now, what we can do with those critical points is go and say negative infinity to 0, as you can see from our very rough sketch, this graph is decreasing. And from 0 to 2, this graph is increasing. Notice we're just using our critical points. And from 2 to infinity, our graph is decreasing. Now, looking at our graph now, we know that x equals 0, or we could say the max is at x equals 2, minimum at x equals 0. So that's where our critical points are going to be. This is our increasing, decreasing values, and this is going to tell us our max and min based off of our increasing, decreasing values. So we've so far answered part A and B, and we've done part E, but we haven't done C, D, and F. So let's go ahead and do that. Now to find C, D, and F, we need to take the second derivative of each one. So that's going to give us negative 12x plus 12. We're now going to go ahead and solve this. So negative 12x plus 12 equals 0. X is equal to x is equal to 1. So this is our point of inflection. Now, because we have an idea of what our graph's going to look like already, we know that from negative infinity to 1, this is going to be concave up. And from 1 to infinity, it's going to be concave down. And the way we know this is, again, if we look at our very, very rough sketch over here, you know that from negative infinity over here to 1, it's concave up, because if you take a look, this graph is facing upwards. And from 1 to infinity, it's going concave down. So that's going to give us our concavity. The last thing we need to identify is that actually we've already done it, point of inflection is at 1. So that's that example. Let's go ahead and take a look at the next one. This one just says find all inflection points. So keep in mind, we don't need to do more than what we're asked to do. It says find all inflection points. So first thing is we're going to find the first derivative. That is 4x to the third power minus 9x squared minus 10x plus 17. That's the first derivative. Second derivative is 12x squared minus 18x minus 10. And next thing we're going to do is we're going to go ahead and start solving this. So first thing I did is I tried to factor everything out. And then I tried using Xbox on this particular graph, or this particular equation, and unfortunately it didn't work. So when that failed, I went ahead and did quadratic formula. And I got x equal to negative 0.43 and x equals 1.93. These gave us all of our points of inflection. Now the question didn't ask us to find when it's concave up or down, but just find inflection points, and that's exactly what we did. So we're going to go ahead and move on. Example 3, I put up here just to make sure I showed you how this might also be asked. Oh, sorry, not this one. Let's go over point of inflection. A point of inflection can occur, but does not always occur, where y double prime is equal to 0, and where y double prime fails to exist. So we're going to do that again, but let's go ahead and look at the second derivative test. It states that if f prime of c is equal to 0, and f double prime of c is less than 0, then f has a local max at x equals c. If f prime of c equals 0, and f double prime of c is greater than 0, then f has a local minimum at x equals c. So I know this is weird, so we're going to look at this table instead. Now, this can help us a lot when we start to look at increasing, decreasing values. Now, if we take a look at this first one, it says y is increasing. So if y is increasing, then y prime is positive. That means if I find a value that's at the critical point, and I substitute it in, then it's positive. That means that the graph is increasing. y is decreasing, that means y prime is negative at that critical point. Y is concave up, y prime is increasing, and y double prime is positive. Lastly, y is concave down, means that y prime is decreasing, and y double prime is negative. So I know that table doesn't exactly make sense, but we're going to have some problems to look at right now. So y equals negative 2x cubed plus 6x squared minus 3. If you notice, this is the same exact question I gave you for one of our earlier examples. Now again, in this case, all we needed to do was find the local extreme values and absolute extrema. So what we did here is all we needed to do was find that first derivative, which we did was negative 6x squared plus 12x. And so when we factored that, we got x equals 0 and x equals 2, and we solved that. And this gave us all of our increasing, decreasing, max, min values. So we're not going to go over that in its entirety because we did it on the earlier example. Example 3 is going to be a little bit different. It says determine the intervals where the graph is concave up and concave down. So remember what it's asking us for, concavity. So that's not first derivative, rather, that's second. So we're going to go ahead and find the first derivative first. Y equals negative 4x cubed plus 12x squared minus 4. So we're going to find y double prime. That's going to be negative 12x squared plus 24x. And so we're going to go ahead and solve that for 0. That's negative 12x squared plus 24x equals 0. We're going to factor out negative 12x from both sides. We're going to get x minus 2 equals 0. So we had x equals 0, x equals 2. So going back to our end behavior, we know this is x to the 4th. So that means it's either both going upwards or both going downwards. And because the lead coefficient is negative, that means we're using this guy. So that means somewhere down the line, our graph is going to go upwards, down, up, and back down over again, almost like an M. So we know that from negative infinity to 0, this is going to be concave down. And from 0 to 2, it's going to be concave up. And from 2 to infinity, it's concave down again. So that's how we determine that concavity. Another thing we could do is make another quick table, which is kind of what we're talking about in our tests. So if we were looking at these things, we know that x is less than 0. And then we know here that from 0 to 2, and x is greater than 2 is what we're looking at. So if we pick a value of x less than 0, say negative 1, and substitute it in, we're going to get a very different value. So let's do that really quickly with x less than 0. Let's choose negative 1. So if we substitute negative 1 in here, if we substitute negative 1 into our second derivative, so this one right here, if we substitute negative 1 squared would be positive 1 times negative 12, so that's negative. And if we substitute negative 1 in here, it's going to be negative times 24, which is negative. So basically this is negative, and since that's negative, then we know that this is concave down, which we stated already. From 0 to 2, if we substitute 1, because that's in between 0 and 2, we get from, again, the second derivative, we get negative 12 plus positive 24. So 24 minus 12 is positive. So we know that's concave up. And if we do the same thing here, that'll be negative. So that's kind of how we're using these tests. So let's look at another example. Now notice this one says find all points of inflection. That's the second derivative. So we're going to go ahead and find the first and second derivative here. We get y prime is equal to derivative of the first times the second plus derivative of the second times the first. That's the first derivative. Second derivative, 1 times e to the x is just e to the x. So derivative of e to the x is e to the x. Plus, if you take a look at the next value we're taking the derivative of, that's the same exact thing as our original. So we're just going to rewrite that derivative, which is the same as y prime. So here we get 2e to the x plus x e to the x. We're going to set that equal to 0. We're going to subtract 2e to the x to both sides, my apologies. We are going to factor out e to the x from both sides, from both items. So e to the x times 2 plus x equals 0. We're going to divide by e to the x to both sides. We get 2 plus x equals 0. And therefore x is equal to negative 2. And that's going to be our points of inflection. That's our only one. So to find out what the real thing is, like what's the ordered pair, we're going to take that and we're going to substitute it in to the original. So that would be negative 2e to the negative 2. And that's our point of inflection and its ordered pair. So let's take a look at this problem. It says where f prime are 0, positive, and negative. So we're basically looking at this graph. We're trying to find out where the derivative is 0, positive, and negative. So for part A, I'm going to do an all red, and part B, we're going to do an all blue. Now, f prime, again, when we find out when f prime is 0, those are giving us our critical points. It tells us when this graph has a max or min. So right here, this is at a min. So that's going to be, so f prime equals 0 at x equals negative 1.25, 0, and 1.25. Because you'll notice it crossed here at negative 1.25, crossed at 0, and at positive 1.25. So that's where f prime is 0. F prime is positive. That means it's increasing from negative 1.25 to 0 and 1.25 to infinity. Because you'll notice at those intervals, your graph, your f prime, is increasing. F prime is negative when your graph is decreasing. So from negative infinity to negative 1.25 and 0 to 1.25. So for f double prime, it's equal to 0 at x equals, notice this time we're trying to find out when it changes concavity. So when it's equal to 0, that gives us our point of inflection. So we're looking at our graph and we're trying to find out when it changes concavity. So for me, it changes concavity, notice from here, it's concave up, and then about here it changes. And then from here to about here, it was concave down, but then it changed. And then from here to here, it went up, concave up, and never changed again. So for this particular one, f double prime equals 0 at x equals negative 1/2. And x equals 1/2. Okay, So moving forward, f double prime is positive. That means it's concave up from the intervals of negative. It's concave up from negative infinity to about negative 1/2, and from 1/2 to infinity. F double prime is negative, means it's concave down from negative 1/2 to 1/2. And that's it. Now moving forward, let's look at another example. I know we're doing this a little fast, but I want to make sure you have time to ask questions in class. Now, velocity, they want to know when the velocity is equal to 0. Keep this in mind. Velocity is the first derivative of displacement. So velocity is the first derivative. That means it's when we hit a max or a min. So we need to find out when this is going to hit a max. So to me, this hits a max at about x equals 4. So right around here, it hits a max on our graph. Okay. Oh, I forgot. Over here, it hits a min at about x equals negative 2. And finally, this hits a min again at x equals 12. So these are the 3 points when the velocity would be equal to 0 because it's either a max or a min. This over here doesn't count because it's still iffy. Didn't really make the graph wasn't very definitive there. Now acceleration, which we're going to do in red. Acceleration tells us when this graph is going to change concavity. So if we trace the graph from here to here, it's concave up, and about halfway through, I'd say at about 1.5, right here, it changes. It was going concave up, now it's going concave down, and about here, which is about 5.2, 5.1, give or take, to about 8, it's concave up, and then from 8 to about 11, it's concave down again. If you see from here to here, it's going downwards. And then from 8 to about 11, actually not 11, 13, it changes again. It was going concave up here, and now at 13 it goes concave about down. So that's the areas where it's going to be 0. So let me rewrite that. So velocity equals 0 at x equals negative 0.2, 4, and 12. And the acceleration is 0 at x equals 1.5, 5.2, 8, and 13. Okay, so finally, last problem, we're going to sketch a graph of f. So given f prime of x and f double prime, sketch a graph of f that passes through the point P. So bear with me here. First thing I want to do is focus on our f prime graph, which is in blue. So we'll stick to blue here. Now, that's a derivative. When we found critical points, it means that these critical points cross through 0. That means this point right here is something. This point right here is something. And this point right here is something. So that means these 3 points are going to give us some kind of maximum or minimum. The way we determine that is we start to take a look at what happens after the fact. So we know that this right here must have been a max because it's supposed to cross through P. We also know it's a max because if we look at what happens after, it's negative. That must have meant it was decreasing at that point. So from here, it must have been decreasing up to about here. And you'll notice that we were decreasing up until here because even from here to here, which I'm going to erase this little line again in a second, it's still negative. That means it was still decreasing. And at this point, we know it was probably our min. After this, we know that after that critical point in blue, this thing is positive from here to here. That means from here on, it should have been increasing, which is why this right here is going to be our max as well. Now notice I did that solely based off of f prime graph. So now let's take a look in red at f double prime. Now f double prime, keep in mind, these points right here tell us when it's a point of inflection. That means that's when the graph changes concavity. So if we mark that on our graph, that means about here and about here, our graph should have changed concavity. So from our point P to that first point of inflection, this was all concave down. Notice from here to here, it changed to concave up. And then after that point of inflection, it changed to concave down again. So this dark red graph is going to be our sketch of f. So that's all for now. You'll have plenty of time to do this in class, but we'll take care of that in class. That's all for now. I'll see you guys next time.